Good morning, everyone. You will be hearing a presentation from Professor Jen-Jee Chen. Professor Chen is currently an associate professor from National Yang-Ming Jiao-Tong University. His research interests include AIoT, 5G wireless communications and networks, robotics, and assistive application, and mobile computing. Today, he's going to give us a presentation entitled Using AI and V2X to Provide Driving Assistance. Ladies and gentlemen, let's welcome Professor Chen.
Good morning, everyone. My name is Jen-Jee Chen from National Yang-Ming Jiao-Tong University, Taiwan. Today, I would like to share some of our research results, in which we use AI and V2X to provide driving assistance. Here is today's outline. First, I will give some preliminaries for everyone to quickly understand the backgrounds. Then, the motivation of this research will be illustrated. I will also explain the proposed system architecture and methods. After that, the field trial and experimental results will be shown. Let you see what our team have done. Let's first imagine the situation when we driving a car on the road. As shown in the figure, assume we are in car A, then we can see some vehicles in front of us, such as vehicle B, C, D, and E, and some are near to us, such as F, but out of our field of view. To protect ourselves, almost all drivers install a driving recorder for the cars. With traditional AI, vehicles in our field of view can be identified. A warning can be given when some vehicle is too close to us. An emergent warning is what multimedia AI can provide us. But is it possible to do more for a driver? Except the driving recorder, there are actually lots of sensors in a vehicle. If vehicles can share this information with neighboring vehicles with radio communications, for instance, information such as speed, driving intention, vehicle status, and its profiles, it will be helpful. In fact, we can do more to assist drivers with this radio and camera information to keep their safety. On the right-hand side of the figure, by fusing camera information and vehicle's profile and status information, we can identify each vehicle in the field of view and know their driving intention. For example, the white vehicle speed is 53 km per hour, and it will turn left after 20 meters. The black vehicle, car B, its speed is 42 km per hour, and it is braking. Through V2X communications, vehicle A can get its neighboring vehicle's information from received radio packets. These information are such as plate number, color, size, location, and driving status. Through multimedia AI, vehicle A can identify vehicles in front of it and get their information, such as plate number, color, size, distance, and angle. By fusing all this camera and radio information, we want to provide a more complete information to assist drivers' driving safety. Before going on, I would like to briefly introduce the concept of V2X for some of the audiences who are not familiar to it. V2X means vehicle to everything. The concept is that in the near future, vehicles can exchange information with other vehicles, with infrastructure, and with pedestrians via radio communications. There are three types of V2X. The first is vehicle-to-vehicle communications. In this case, two vehicles can communicate to each other directly. The second is vehicle-to-infrastructure. In this scenario, a vehicle can interact with infrastructure such as traffic signals. The last is vehicle-to-pedestrians. In this scenario, vehicles and pedestrians can exchange their information. So, vehicle-to-everything, V2X in short, includes all above scenarios, V2V, V2I, and V2P. So far, there are two main strings for V2X. One is DSRC, which is also known as IEEE L2.11p. The other is 3GPP LTE A Pro and 5G. Since release 14, LTE A Pro starts to support V2X. It is for sure that in the coming 5G era, 3GPP will still support V2X. So, future cellular system will provide strong ecosystem support for V2X. If any one of you are interested in the detail of V2X, you can study DSRC or 3GPP spec. Here I will not go into the detail of both protocols because of the limited time. In this slide, I use examples to explain our problem. I'm driving a vehicle. In my field of view, there are 4 vehicles in front of me. How do I know the driving status and the driving intention of this black vehicle? And others through camera and radio information. If there is only one vehicle in our field of view and this is also the only one among us, this question is simple. We will only see one red vehicle and only receive one kind of radio packet. Inside the packet, the vehicle shares its profile and says its speed is 60 km/h. So, the radio information must belong to the red vehicle. We can pair the packet and the red car and then tag the red car with the driving status as shown in the figure. However, if there are 2 vehicles in our field of view, one is red, the other is silver. Also, we receive 2 types of radio packets. One says its speed is 60 km/h. The other says its speed is 70 km/h. Now, how do we pair the right vehicle with the right radio packet? Which packet is sent by the red vehicle and which of that is from the silver one? This question is hard because communication are usually non-line of sight. In fact, in a more general case, there would be more than two types of radio packets, because some of the neighboring vehicles may not be in our field of view, but near to us. So, this is a challenging problem. The processing procedure of our methods are described as follows. First, a deep learning algorithm keeps running to identify and tracking calls from the input video streaming. In our implementation, at that time, we use YOLO v3 for real-time detection and tracking. At the same time, each vehicle periodically broadcasts its profile and driving status via V2X communications. Car profile includes information such as plate number, color, car type, and GPS location. Driving status include vehicle's current speed, braking status, rotation, and turning status. Then, our methods fuse the camera information and radio information via pairing the vehicle object in the camera frame and the V2X radio packets. Finally, we tag right information to right vehicle object. This figure shows the original YOLO v1 model architecture. The full name of YOLO is You Only Look Once, means that for every figure, it can identify objects by one-time calculation. Too much iterative calculations are not needed, so it can support real-time object detection. Here are the detailed fusion procedure of our first method. We assume that each car is equipped with OBU and V2X communication interface. The onboard unit, OBU in short, is equipped with camera, GPS, and magnetometer. So, for vehicle A, its input includes the front camera's video stream, its own GPS location and orientation, and neighbor vehicles' radio packets received from V2X interface. Inside the radio packet, it is one of neighboring vehicles' profile and sensing information from the OBU. YOLO is responsible for processing the video stream. Sensing and received broadcast data will go through a data pre-processing procedure first. Then, for any possible pairing, for example, in this image, we can see 4 vehicles, B, C, D, and E. Since there are 5 neighboring cars, we will receive 5 different V2X broadcasting packets: B1, B2, B3, B4, and B5. Our goal is to pairing the vehicle object in the image with correct broadcasting packet. So, here we will first calculate the weight for any 2 possible pairing. Finally, the mapping decision algorithm will conduct the final pairing. Which pair right vehicle object to write car profile and driving status. Because of different notations, here we assume that we are driving vehicle X. Here, OBU, the vehicle X can obtain its location and orientation. Vehicle X can also receive a number of broadcast packets from neighboring cars. We identify each packet by using notation BJ. Then, data preprocessing module will derive two features between X and any packet BJ. They are distance and angle. The equations are as follows. Here angle is a relational angle between vehicle X and BJ. This slide shows how weight calculation module derives the weight between any vehicle BJ in the field of view and any broadcast packet BI from the neighboring cars. In fact, the weight calculation is comparing the similarity of the content of a broadcast packet and a vehicle object in the camera. To calculate the similarity, we consider 5 features. The first one is the plate number. So in the first equation, we calculate the number of matched characters between vehicle BJ and broadcast packet BI. Here we normalize it by dividing the number of characters of a plate number. The second is the color of the vehicle. Here we calculate the square root of the RGB color difference between vehicle BJ and packet BI. Smaller difference will get a higher weight. The third weight is the car type. If the vehicle type of vehicle BJ and broadcast packet BI are the same, then the weight of car type equals to 1. Otherwise, the weight of car type is 0. The fourth weight is the distance. We calculate the difference in distance between GPS measure and camera measure. The weight getting large when the distance difference is small. The last weight is the angle. We calculate the difference in angle between a magnetometer measure and a camera measure. Finally, we sum up all the 5 weights to derive Wij, which is the weight when pairing vehicle BJ in the camera and broadcast packet BI sent by some neighboring car. Then, for broadcast packet BI, we define its confidence as follows. The confidence value is high when packet BI is very similar to one vehicle object and very different from the others. Here we design two mapping decision algorithms. One is short-term pairing, the other is long-term pairing. Short-term pairing considers only the latest camera video frame and the received broadcast packets. So, highest confidence value Ci of t will be paired first. For sure, packet Bi will be paired with the vehicle Vj star when Wij star is the highest weight in all Wij. And then the confidence value of the remaining broadcast packets. will be updated. After completing the update, the pairing procedure will be executed repeatedly. Compared to short-term pairing, the long-term pairing will consider the historical pairing result. The long-term pairing result will be stored in a vehicle LP of T-1. Each element in LP of T-1 is a triplet: BI, BJ, W prime IJ, where W prime IJ is a long-term weighting value. In the long-term pairing, we will take LP of T-1 and short-term pairing result SP of T into consideration. There will be 4 possible cases when we compare LP of T-1 and SP of T. The first one is that packet BI and vehicle VJ are paired together in both results. Then we keep the pairing results and update only W prime IJ of T as follows. Different from the first case, in case 2, we will find a broadcast packet BI is paired with different vehicles in SP of T and LP of T-1. For example, in short-term pairing, BI is paired with vehicle VJ, but in long-term pairing, BI is paired with vehicle VK. When this occurs, if 1 minus alpha multiplied by W prime JK is greater than or equal to Wij, then we keep the long-term pairing result as the final result. Otherwise, we update long-term pairing result by copying the short-term pairing result. That is, BI is paired with vehicle VJ instead of VK. Then we keep the pairing result and update only W prime IJ of T as follows. In case 3, we find a pairing result for packet BI, but we cannot find it in short-term pairing results. In this case, we will keep the pairing result in LP of T, but update its weight as the original weight multiplied by 1 minus alpha. This case may occur when the broadcast packet is not received by vehicle X because of interference, or when the vehicle VJ is far from the vehicle X at time T, so they cannot hear each other. The last case is that we can find a pairing result for packet BI in short-term pairing, but we cannot find it in long-term pairing result. For this case, we will accept this new pairing and insert it into LP of T. After above steps, we got the long-term pairing result LP of T for time T. Here, let's see a short film. In this film, we do field trial for above proposed method.
We conduct the field trial in a real-world scenario. 3 cars were equipped with GPS and IU sensors, one of which was equipped with Z camera to capture the surrounding images. By this field trial visualization, we've shown that through our data fusion and real-time V2V communications, we can let a car visually see the driving status of its surrounding cars.
Okay. Here are some details of our field trial. As shown in Figure A, before using our data fusion algorithm with camera AI, with camera AI, we can only identify vehicles, track vehicles, and get camera measure distance and orientation. With our data fusion algorithm, because car B and car C share their information with V2X communications as shown in Figure B, we can correctly tag each of their car profiles on the right car. Since car A is not equipped with V2X interface, no car profile is tagged for it. Like above two figures, Figure C and D show similar results before and after data fusion results. In above field trial, we prove that our idea can work on the real road, but we found two problems. The first one is that we take lots of time for the experiments, but only get very limited data sets. The other is that collecting such real data set costs lots of money. In fact, in that experiment, we hired two Uber drivers for several days and do the experiment. To collect data sets, a traditional way is that the researchers driving their vehicles on the road and then collecting the sensory data of the vehicle and the front camera's video or LiDAR data. After getting the real data sets, we can take them back to the laboratory and test the design algorithm's performance. However, by this way, we can only get limited data sets and limited scenarios. So, to solve this problem, we have developed a simulation platform that enables V2X communications. And then, via the platform, we can collect rich kinds of data sets by simply changing the simulation parameters and doing simulations. To develop the simulator, we use the open source platform Kala as the base, and then extend and implement several modules to build a V2X simulation framework. Here I will not spend too much time to explain about the detail of the simulator. This figure shows the system architecture of the simulator. The simulator is composed of three layers: configuration layer, sensor layer, and the output layer. In the configuration layer, there are four modules: weather module, map module, spawn module, and self-driving modules. The weather module is responsible for producing different parameters for different weather. Weathers such as sunny day and rainy day are provided. The second module in the configuration layer is the map module, or called geographic information module. It is to provide different road maps and geographic information. Here are some examples. Spawn module, or the vehicle flow module, can support us to generate different degrees of vehicle flows. Here are the examples of light traffic, medium traffic, and heavy traffic. The last module in the configuration layer is the self-driving module. In the module, the developer can develop his or her own autonomous driving algorithm or use the default method. The sensor layer is divided into three modules. They are the camera image module, V2X communication module, and sensor module. The camera image module is to collect the image data of the main vehicle. Here we can see some examples. The figure in the left-hand side is the front camera view of the main vehicle, and the figure in the right-hand side is the back camera view. The second module is the V2X communication module. The module is responsible to simulate V2X communications. Currently, we support Wi-Fi and cellular V2X communications. The module is developed by referring to the real statistical results. So, the delay and jitter characteristics of these radio communications are considered in this module. The last module in the sensor layer is the sensor module. So far, GPS sensor, speed sensor, and orientation sensors are supported. The only module in the output module is the dataset generation module, which logs the image and sensor readings of the main vehicle and records the profiles and sensory data of surrounding vehicles from the V2X communication. Finally, the dataset generation module will package this log data as the data sets. So, with the simulator, we can get data sets in rich bound of scenarios, such as different road maps, different degree of vehicle flows, light traffic, medium traffic, and heavy traffic. Using these data sets as the input, advanced algorithms can be tested and check the performance in different scenarios. So here, let me show a use case of the V2X simulation framework by redoing the aforementioned experiment. As shown in the right-hand side, here are some frames from our simulated datasets. We have also redone the experiments to evaluate our fusion algorithm. From the figure on the right-hand side, we can see that the car profiles are correctly tagged on the right car. Here, 97, 25, and 137 are these vehicles' virtual plate numbers. In the following, we would like to solve the same problem but with more AI. Here, in the red box, we show an alternative architecture of our second method. We design a mapping decision feedback neural network, MDFNN in short, which is inspired by RNN. The input data is the sensory data of vehicles and the mapping decision results in the near past. Via the MDFNN, we can position the vehicle in a frame for each broadcast packet. In the image, we can also position the vehicle objects with Euro. Then both results will go into the mapping decision block. The block will map and fuse both results. This is the network model. This is how we design the MDFNN. Input data is the sensory data of vehicle X and broadcast packet BI, and the past mapping decision result of BI. Here we illustrate the concept of our car position estimation method MDFNN. The input of the MDFNN include the location and speed information inside packet BI. Vehicle X speed and orientation, and the past positioning result of packet BI. All these input data are all normalized. Then MDFNN will predict the current position of BI as shown in the figure. Okay, let's check an example and see how the whole system works for a packet BI. Assume the packet BI is sent by the black vehicle, but how do we identify BI is sent by it and then tag inside information with the black car? We will divide the whole screen into grids. For example, this image is divided into 5 by 5 grids. Each cell in the grids is mapping to a neuron in the MDFNN. Okay. Since BI is sent by the black car, so the ground truth shall be like this. The grids which contains the black car, the value will be 1. Other grids will be 0. Here we have to note that there is one more neuron called outside. This is for the packet from the vehicle which is not in our field of view. So, if the MDFNN is well trained, after the calculation of MDFNN, we will get a result like this. Here we can try to position the packet PI. We can see there are higher probability in these 4 grids. MDFNN thinks the owner of packet BI shall be in these 4 grids. Euro also generates an output like this. It identifies there are 4 vehicles in the frame. MDFNN positions the target vehicle using sensory data BI. Euro also identifies vehicle objects on the screen. Then, in the mapping decision phase, It is responsible for deciding which car in the image is the target vehicle of packet BI. Obviously, there is a large probability that packet BI's owner is the black car. Then we can augment the vehicle information and driving status on the black vehicle. Here is the loss function we designed for NDF-NN training. There are two parts. One is the loss for the grid in image. The other is the loss for the outside area. Here is our experimental results by using our simulated data set. Let's see. Okay, so how about the accuracy? Here is the setting of our experiment. We deploy 5 cars surrounding the main car. We take image and receive broadcast packets once per hour. The car only receives broadcasts from cars which is near enough. The distance needed to be less than 30 meters in our setting. There are about 1,400 images and 6,700 broadcast packets in the data set. We can see that compared to RNN and baseline method, our method can get an improvement by about 30% accuracy. Here we can also see the effect of grid numbers. As the grid number increases, the accuracy also raises, but the performance converges after 11 by 11 grids. In this speech, we discuss an interesting vehicle object and the broadcasting packet pairing problem. Two methods are proposed. One is AI for object detection plus algorithm-based fusion, and the other is an almost AI method. With simulated data set, we show that both methods can work. Okay, thank you for your listening. If you have any question, you can give me a mail. My email address is as follows. Okay, this is my email address. So any question?